Good morning, I'm Jeff Gennari, and I'm going to be talking about our work in property-directed test case generation. So let's get into it. Big picture, what are we trying to do? We're trying to simplify the process of software evaluation by generating actionable, executable artifacts to prove the properties do exist in software. So if you think about other ways that you do software evaluation and analysis, of course we have testing, where you have a human analyst, a software development engineer, and test sitting somewhere analyzing an input domain, formulating test cases, and supplying that to a program to see if they can trigger a defect or reach some critical aspect of the code to exercise behavior. This tends to be a human-driven process, a lot of trial and error, can be very complex. If you have complex input domains, it can be very trying to get testing correct. Other tools exist to help with this, notably model checkers. Sagar talked about model checking a little bit. The idea here is we create an abstraction of the code that we want to test or the system we want to test. Specify some properties in a mathematical language like a temporal logic. Run that through a model checker which exhaustively checks every state and tells us whether or not we can satisfy a given property or not. One of the nice things about model checkers is if you can satisfy a property, you get a trace. The trace tells you exactly what steps you took through your model to satisfy that property. Unfortunately, these tend to be very abstract. So model checkers, they work on logics. You build a model of the program. It's not the actual program. So there's this translation step that still requires a human analyst to sit down with the model checker output and translate that into something more concrete. This requires quite a bit of expertise. Some of these systems are very complex. For example, the spin model checkers it's been around for decades and has books written about it. Not terribly easy. So what is property-directed test case generation? The idea here is, to some extent, to make things as easy on the analyst as possible by freeing them from having to reason through counterexamples and traces produced by a model checker. The big high-level flow is take the program source code and instrument it with special annotations. I'll get into what those are in a second. Those annotations basically distinguish in the source code areas of interest. These can be parts of the code that you suspect to have a defect. They can be parts of the code that represent some interesting behavior that you want to test. Put that into the PDTG prototype tool that we've built, and out will pop an executable that will deterministically execute the code to trigger that property. So no guesswork by the human. You get an executable. You can take that executable and drop it into a debugger, drop it into an analysis environment, and go about your merry way trying to correct your problems. Going a little bit under the hood, this is the high-level schematic of what we actually did. So we still use model checking. In particular, we use a tool called the Seahorn Model Checker that was developed both here at the SEI in collaboration with other folks, I believe at NASA. Seahorn's nice. It's been competitive in a number of formal analysis contests. One of the nice things about Seahorn is that you feed into it source code that's annotated a certain way, so that you kind of bypass this step of creating an abstract model. Everything is turned into LLVM bitcode, and the analysis works on the bitcode itself. So it's very close to the source code. So you instrument your code using Seahorn's annotations, run it through Seahorn, and you get a trace. This trace is still very abstract, and it's incomplete, but it does show you how you would get to the property that you care about. The next step here, the next two steps actually, are where we spent, I believe, the majority of our time. It's in generating the executable harness and then turning that back into an executable using a symbolic execution tool called CLE, which is publicly available. The executable harness is the step where we have to reason about all the dependencies that might not be present in the program. So imagine imported library calls, sources of non-determinism, where you don't necessarily have an implementation. We bring that all in, and through analysis, build up stub implementations of those functions that will make the code go in a certain direction, make control flow go in a certain direction. So to show you what this looks like with just a little bit of code, The verifier error that you see in big capital letters is actually part of Seahorn's syntax. You instrument your code with those function calls. Seahorn will try to reason through the bit code. This will be compiled to LLVM bit code. Seahorn will reason through that, trying to figure out what control flow path will reach the verifier error call. In this particular case, we have two dependencies to get the verifier error. We have to call get input twice. The first call has to return the value 1234 in hexadecimal notation. The second call has to return 8765 in hex. And now imagine that get input is some external function. We don't have the implementation. Maybe it's a network call or something like that. So what we do is we look at what the requirements of the program are, reason through it, and generate a piece of code. It's here in source code. We actually generate it in LLVM bit code. But it would look like the bottom here. This would be considered the harness, where you can see that there are two, on subsequent calls to this function, you return 1234 and the other value that you need. And so with this weaved into the program, when you run this code now, you'll deterministically get to the verifier error call without having these external dependencies. They're simplifying your analysis. Along the way of doing this, we learned quite a bit about the challenges of trying to construct these executable harnesses. One thing that we're still kind of working through now is that people do funny things with memory. So for example, we ran the tool on the Linux driver verification project, which is a set of benchmark file Linux drivers to test formal analysis tools. And one of the things we discovered is that any external function that operates on memory isn't as predictable or easy to deal with as we would like it to be. So with Linux pointers, sometimes you have encoded in the pointer value itself error information if there's a problem. In this particular example, we found the value 2012 was actually encoded as part of the pointer. I guess that the entire address space for the pointer is rarely used. This makes sense if you think about userland, kernel-land, segmenting of memory. And so you have these extra bits laying around, and so they repurpose them like this. So what we've done now is built in some exceptional cases to handle this kind of thing. But future work for us is trying to figure out a more general solution to handle these side cases so that every time we run into them, we don't have to engineer in a way to get around that. Another application near and dear to my heart that we use this technology for is malware analysis. And so when you do malware analysis, it's often one way to do it is to identify some behavior that you care about in a file. And then try to zero in on that behavior, be it the information stealing piece, some backdoor, whatever. Try to zero in on that and throw it into an analysis environment and make it actually execute so you can observe it, you can collect traffic or indicators or whatever else you want to do. In practice, that's really hard because malware often has external dependencies. It's waiting for some kind of special command. There's some environmental trigger like the time of day. And so there's all kinds of non-determinism that makes it really hard to do this kind of analysis. But with PDTG, what we can do is we can generate an executable that will trigger the behavior that we want to study in depth, hand that to our malware analysts, let them drop it into their other tools, and then go about completing the analysis. We actually did this on a tool called the Ghost Rat, which has been a publicly available piece of malware for a long time. Source code's available. And so we fetched that, found the interesting bits, instrumented it, put it through, and were able to generate end-to-end executables that would skip all the parts where it had to communicate with an adversary and just execute the actual malicious parts. So this is particularly interesting. Finally, I want to talk about our results from the driver verification benchmark. So there are 27 files in the benchmark. Of that 27, 13 we were able to generate harness. So the benchmarks have known bugs seeded throughout them and other interesting pieces of behavior. We used PDTG to instrument the benchmarks to trigger the bugs. We were able to do that successfully. What I mean successfully, I mean generate the harness and actually trigger the code that is buggy in 13 of the 27 of the 27 cases. There were 11 that I'll call to be determined because all indications are the technique is going to work, but the limitations of the machines that we were running, which were laptops, commodity hardware, didn't work out for us, so we need to do some more investigation there. And then the 3 at the end, I'll say we need those on some preliminary analysis have to deal with the memory issues like the special values and pointers that I mentioned earlier in the talk. So those are situations that we know about and that we need to go and address as part of our future work. Finally, I want to thank our collaborators, both here at Carnegie Mellon and at NASA, and I want to thank Dr. Ari Gerfinkel, who was the principal investigator for this work, now our faculty at the University of Waterloo, and welcome any questions.